Hello everyone, welcome to the YouTube channel I am Chemistry. So today's topic is Maxwell's relation. Maxwell's relations are a topic in chemical thermodynamics of physical chemistry. So we are today expecting that Maxwell's relations is all clear in our minds. So there are four Maxwell's relations which are studied as which there are generally four Maxwell's relations in which the various expressions connecting internal energy, Gibbs free energy, work function, and not work function, Helmholtz free energy, enthalpy. These are connected by putting several parameters with temperature, pressure, volume, etc. With these three entropy, with these four types of things, so they are written as the first is du is equal to tds minus pdv. This is the first relation for the internal energy. Then we have the second dh. This is for change in enthalpy, so small change in enthalpy. This is tds plus vdp. This is second equation. Then we have third. The third is small change in Helmholtz free energy, which is minus sdt plus not plus minus pdv. This is, let's call it, third equation. And the fourth relation is for small change in Gibbs free energy, which is minus sdt plus vdp. This is fourth, let's call it fourth equation. So now we have these four equations. So the first thing which comes in our mind that how to learn these four relations, because these are not very appropriate, and we have to learn these because these four are used in the all the relationships we are doing in these things. So there is an analogy used by several times, which is as follows, this is like there is a Maxwell square. This is a Maxwell square. So as we see that in this Maxwell square we have the four parameters, that is volume, temperature, pressure, entropy. These are written on in such a way at the corners of that rectangle, and the four important things, that is internal energy, enthalpy, Helmholtz free energy, and the Gibbs free energy, are written as follows. There is Helmholtz free energy, there is internal energy, and there is Gibbs free energy, and the last one is enthalpy. So let's take a look at how to use this to acquire these four relations. So in these there is a rule that the property heading the arrow is taken as negative. Head of arrow is taken as negative, and the tail of arrow is taken as positive. So let's take a look at these things. Now we have with the use of this, let's calculate this. So I am going to calculate these things with the help of this square. So the first of all, I have let's calculate for du, which is change in internal energy. So for this thing we have to go through this line, that is where is u is written, where the u is written, those two are written as ds and dv, change in entropy and change in volume first of all. Then we have volume in front, in the diagonal relationship of volume we have p, that is written, and in the uh, diagonal relationship of s we have t. Now we have a thing that what is between, now we have to put sign equivalent. So as I told you that we have to put minus to the arrow which is coming towards the head. So p dv, that in that way that the tail has positive but the v is on that side, as we are concerning internal energy relation. So this is v, and we put the, this is at first relation, this is the first relation, in that way. Now let's take a look at dh. Similarly, let's go to dh, where we have, let's go to dh where we have entropy and pressure. So let's again ds and dp. Now in entropy, in the front of entropy we have, in diagonal relationship we have t, and in the diagonal relationship with the p we have v. And now what is the sign between them? Then again this thing arrives, but because in this case the arrow is emerging from this, so it is taken as positive. I hope these things are clearing in your mind. And let's do similarly, let's do it for dA, which is d, where is dA? So dv and dt. In diagonal relationship of v we have p, and in diagonal relationship of t we have s. And now let's take a look at the sign between them. So p dv and s dt. So in both these cases the arrow is coming towards them, so they are taken as negative, and it is also taken as negative because the arrow is emerging towards them, v and t. And the fourth relation I am writing it here, that dg, the change in Gibbs free energy, which is written as g, we have dp, change in pressure and change in temperature. So temperature s and pressure we have v, and let's put the sign between them. It is v dp minus s dt. There is minus sign comes between them because the minus is the because the entropy have emerging arrow. Okay, so this is the fourth relation. Now we are going to use these four relations, and we have to calculate what is the relationship between these two equations, like first, second, third. For first, second, we are going that in first, second, what is the relation, first, third, what is the relation, then first then second and third, what is the relation between second and fourth, second and third. Yes, second and third. And then we are going to put third and fourth. What is the relation between them? Like suppose this is later task, but first of all we have to find what is the relation between individually. They are individually what the relations comes in them. So in the equation first we have like du is equal to T ds minus my P dv. So first of all, let's put v as constant, and in this we have supposed v is constant, and then then entropy as constant. So we have like in the first thing, like we have to do du by d. When we have put volume constant, this whole term is 0, so then ds is equal to t. So this is the first equation we have like in this at constant volume. And then we have, if we put entropy constant, then this whole term is 0, then du by dv, del u by del v, what we call it, minus p for our consequence at constant entropy. So this is the equation which we have in this like these are the relations but this is not conclusion. So now we are going to differentiate this relation with respect to change in volume. So the like d by dv of del u by del s is equal to on because we have to do it in both sides, del t by del v at constant, because if we have do it change in volume, so we have to put one thing is constant, that is entropy in this relation. So this is written as I am writing it on that side, d square u by d del v del s is equal to del t by del v at constant entropy. Then this is I am calling it equation A. So let's go to the next page. Now we have to do the same procedure to this relation. So if as below, as in the denominator we have del v, so we are going to differentiate it with respect to entropy. So del u with respect to del v del s is equal to, and what we have at that side, minus p, so minus dp del p by del s at constant, as we have to change we have to do this with respect to change in entropy. So we have to put constant volume constant at volume at constant measure, then this is the relation. So as we see that d square u, this is d square u, so as we see that this and this are equal in A and B, so from A and B, as the left hand side are equal, so the right hand sides are also equal to each other, which are del t by del v by del t by del v at s, del t by del v at constant s is equal to del p by del s at constant v. This is going to be our fifth equation. This is going to be fifth equation, because this is the first relation between Maxwell's parameters with the use of those four Maxwell's relations. This is the fifth Maxwell relation, or we call it first for our convenience. Now we are going towards our next equation, which is for change in enthalpy. Del h is equal to T del s v dp. Del h is equal to T ds plus v dp. T del s plus v del p, whatever you call it, d or del, because both have the same meaning as a small change in that parameter. So let's perform this same operation with these, and we got like at keeping first s constant. If we put s as constant, then we have del h by del p is equal to v, because at constant s this whole term is 0. So this we got at constant s, and then we have and then with p at p constant. So now we have if p is constant, then this whole term is 0, and del h by del s at constant p is equal to t. So this is both are the same. Then we have to do the above operation in a way like differentiate it with respect to s and differentiate it with respect to p, and then putting both the right hand side term, because the left hand side terms are again going to be equal. So let's do it. Del h by del p del s is equal to del v by del s at constant pressure, and for this del square h, we have to do this because we are going to be double derivative. Del square h by del p and del s is equal to del t by del p at constant entropy. At constant entropy. So now because if we are going with respect to one term, then the other term is automatically constant. I think there is no problem coming in front of you while I am going to explain these things. Now as these two are again equal, so these right hand sides are again equal to each other, and this is going to be our next relation, del t by del p at constant s. This is our sixth equation. Let's calculate the relation coming in front of us from the third equation, which is, let's say the third equation, which is the change in Helmholtz free energy, which is minus s del t minus p del v. So let's do for this. First of all, we have first call temperature as constant, and this whole term is 0. Then del A by del V at constant temperature is minus P, and del A, if we call volume as constant, then del this is upon that, and constant volume is equal to minus mass. Then again we are going to double derivative with respect to that term which is not constant in between the previous one, and the thing is like del A by del V del T is equal to minus del P by del, like we have put del T, then del T divide the right hand side also with the del T with at constant volume, and this is again d square A, and del square A by del T del V is equal to minus del S by del V at constant. Let's, because this is with V and this is with T, because the two are very complementary to each other in that relations, for our convenience we usually cram it. Maxwell relations are cramming because in competitive exams we have to put them as usual, and then at that time we have not much enough time to do these on separately on paper and then use them, because in that case we are wasting our time. So we have to usually cram them. So this is the next. Then if these two are equal, because these two are equal again, so we have minus del P by del T at constant volume is equal to minus of del S by del V at constant temperature. Is minus minus is equal to plus, and this is going to be our seventh relation. Okay, now we are going towards the eighth relation, which comes from the fourth equation. So let's show the eighth. Where is the fourth energy, which is for our convenience I am writing it here, minus S dt and is equal to plus V dp. Let's put our page here. Now, performing the same operation, if I put first the temperature as constant, then pressure. If I put temperature as constant temperature, then this is like that. And if I am going to do pressure as constant, del G by del T at constant pressure, then this term is 0 and this is minus S. Then I am going to do a double differentiation with respect to the other term, which is not in the previous one, and which is del square G by del T del P is equal to del V by del T at constant pressure. And for this, again del square G by del T del P is equal to minus del S by del P at constant temperature. So again these two things are equal, and we have got our eighth relation, del V by del T at pressure, constant pressure, is equal to minus of del S by del P at constant temperature. This is going to be our eighth relation. So as you see, we have solved our fourth relations by going through that. First we have to use these four equations, which you easily now calculate from this Maxwell square, for which that you have to learn it, because with the use of that arrow head and blah blah, we have to use in minus plus plus minus minus plus. We have to do it because this is used in if there is a discrepancy in these signs, then the whole thing goes in dot and we have find nothing, and our whole process goes just wasteful. So from equation, first I have to do that. First, if it is constant, then it is 0, and this is du du by TDS is equal to 2. Similarly for this, if it is constant, then it is equal to that thing and that, and you saw that these are the two relations. Then I have that thing like as you see, we have that, and similarly this relation, this seventh relation, sixth relation, and this is now your eighth relation. So these are the four Maxwell relations. The equation 5th, 6th, 7th and 8th are four Maxwell's relation. Then we have to do with the these are the individual equations. Relations comes from the individual equations, but what relation comes when we use the two of the equations. So let's first use the equation first and second. du del u is equal to T del S minus P del V, and the second equation is del H is equal to T del S plus my V del P. So as we see in these two equations, we have one thing is common, that is TDS. So if we are going to take volume as constant and in it then pressure as constant, then we get this term. So there is a relation between two of the different parameters like internal energy and enthalpy. So del U by del S at constant volume, that is going to be 0 and it is T, and del H by del S at constant pressure is equal to T. Okay, and now we are going to do that now we are going to do again, because these two are our right hand side equal, so left hand side are also going to be equal. That is del U by del S at constant volume is equal to del H by del S at constant pressure. So this is going to be our ninth equation. This is between two of them. So now we are going to find a relation between this is the relation between first and the second equation. Now we are going to find a relation between first and third equation. So let I call it between first and second, and we are going to know first and third. So in first and third equation, let's write it as again du is equal to TDS minus P del V do del whatever, and the third relation is del A is equal to minus S del T minus P del V, which is going to be then again we have to first find which is common in both these, that is this. So at del U by del S at constant volume, if we put one volume as constant, then this whole term is 0 and this is equal to T, because this term is left and pivot. And then del A by del, if again we put volume as constant, then del T at constant volume is equal to at constant volume. Then we are going to do equal at minus S. No, this is not going to be so. We have a ds, and we are taking it wrong here, so just put it as follows. But there is a discrepancy, as you see in here, that TDS minus PdV and TDS plus VdP, when we are taking V as constant, that this whole term is 0 and it is equal to T, and we are taking P as constant, then this is equal to T. Okay, then in this relation, when we are taking V as constant, then this is equal to T, and when we are taking no, we have to do it again. So from equations first and third, what we have to do is that So by doing the same procedure like I have done in from equation first and second, we have found that the other relation is del U by del V at constant entropy is equal to del A by del V at constant temperature. This is going to be our eighth relation. Then from equation second and second and fourth, because second and fourth is we have two terms which are common, and by operating the same operation we find that from second and fourth equation we have found that we have found this relation by operating as such operation del H by del P at constant entropy is equal to del G by del P at constant temperature. You are getting me, I hope. Then this is going to be our ninth relation, and the final one is between from equation third and fourth, which is going to be again between G and A, which is del A by del T at constant volume is equal to del G by del T at constant pressure, which is 10th relation. So we have 10 relations which are like first we have got four relations from the first, which are used from our Maxwell's square, which is like that, and you know that analogy, that there are arrows and from emerging negative and positive sign, that is like you have like these parameters: entropy, volume, pressure, temperature, internal energy, Helmholtz free energy, enthalpy, and Gibbs free energy. Then using this analogy we are going to find these four relations, and with the help of these four relations we have find these terms, like this is the first relation. Then we have found that thing, sixth relation. Then we have found this seventh relation, and then we have found this eighth relation, and from the other analogy we have found this. There is a relation we have also, I forgot about to tell. This is the eighth relation, this is the ninth relation, and this is the 10th, 11th, and this is the 12th relation. So we have in total 12 Maxwell equations which we have to remember, and with the use of these 12 Maxwell equations, which are used in various thermodynamical derivations, which are very useful for us in our CSIR NET GATE, TIFR chemistry, BARC chemistry, and other government exams, government institutions, and also to boost our knowledge. You have to go through such events. Hence, I hope you like the material which I have shown you, and the concept, the way of concept I have represented you, the Maxwell's relations. I hope you like it, and this is your own channel, so For further videos and for further boosting your knowledge, subscribe it, and I am here for your help every time. So please subscribe it, like, share, whatever with your friends and in classes. Thank you.